Hallo und herzlich willkommen. Ich begrüße Sie zur letzten Deep Dive Session des heutigen Tages, ein Workshop von Women in AI and Robotics. Nun geht es nochmal um Sprachmodelle wie ChatGPT. Es ist ja umstritten, inwieweit diese in der Lage sind, auch komplexe Konzepte zu erkennen und zu verstehen. In diesem Workshop geht es um die Argumentationsfähigkeiten großer Sprachmodelle. Und es wird darüber diskutiert, welche Grenzen sie haben und welche möglichen Anwendungen es gibt. Speakerin ist Shabnam Sadegharmaki. Sie ist Data Scientist bei Microsoft und beschäftigt sich sehr viel mit Natural Language Processing und Empfehlungssystemen. Und sie ist natürlich Mitglied bei Women in AI and Robotics. Frau Sadegharmaki, the floor is yours.
Hi, thank you, Shad, for your great interview. Without further ado, we can go toward the slide. Yeah, great. First of all, welcome to this talk, the last deep dive session on this TÜV-Verband's AI conference in 2023. So I will be talking about reasoning in large language models. And I am honored to be representing Women in AI and Robotics. We are a German nonprofit charity organization headquartered in Germany, Munich, and with local chapters both in Germany and Canada, with more than 1,200 members around the world. Our mission is to reduce gender gap in artificial intelligence and robotics. So please reach out and get to our expo and the link provided in the expo if you would like to help this cause, or reach out to any of our amazing members in this community that we have built. There are many talented women and experts in industry and also academia. So without further ado, Shad gave a good introduction. So let me introduce myself again. So hi, this is Shabnam Sadegharmaki. I am a data scientist at Microsoft. And today, the specific topics I will be talking about is reasoning. What is reasoning? What benchmarks we will use to, or we are using to assess the capabilities or reasoning capabilities of different models which are solving these kind of tasks. And finally, we will dive into larger language models with the advent of ChatGPT is a very hot topic recently. So let's dive in. I would like to start by giving some textbook philosophy definitions of reasoning, and you will see where I will get into afterwards. So the most straightforward definition is reasoning is to discover valid conclusions by applying logic. So it sounds easy, but as you can imagine, devil is in the details. That's why. So we don't know what kind of logic we can use, what kind of conclusions we can use, that when we are imagining AI in our daily life, or even human cognitive capabilities. So let's get deeper into these definitions. A more concrete definition maybe is reasoning is to infer conclusion from a set of premises consisting of one or more inference steps, where premises and a conclusion are assertions that claim something is true or false about the world. So you can imagine this definition usually is very important when it comes to judgment and evaluation that we are doing day to day. And you can also imagine the kind of AI applications that we can discover or we can create that rely heavily on judgment and evaluation of different systems or different interactions. So let's look at another aspect of reasoning. So from a practical point of view, reasoning is to infer actions from goals and knowledge, which is oriented to deciding whether an action is practically reasonable. This definition is important and gives us why reasoning would be crucial for some of the tasks that we would like AI to solve. We as humans, we use We are doing short-term and long-term planning along the day to complete tasks. And one part of it is to gather goals and knowledges that require planning those actions. So these are all under umbrella of reasoning, which will be crucial for our future AI products. And finally, so there are two more definitions to come. One is reasonings is an essential mental activity when conducting conscious tasks with complex computations. This one is very important as we are trying to solve problems daily and or decision making or even tasks such as persuasion and explaining to others. These are the parts that we are using the reasoning part, the capability of our brain to complete these tasks. And when we are thinking about AI models that are capable of solving some of these problems, so actually we are looking into reasoning. And finally, another aspect, or final aspect, is that with reasoning, you would integrate multiple knowledges to get a new conclusion. So this is in opposed to a direct information or first-hand information to get that conclusion. So human has this capability that can get information from multiple sources and kind of generalize it to a new rule or to a new conclusion. This can be also important for some of the problems that we are trying to solve with AI, the problems that require deduction, puzzle solving, or even common sense. So I told all of these definitions and use cases to tell you when I chose the topic reasoning for this talk. Actually, I'm talking about a broad range of problems that AI can solve, or mimicking or imitating some of the cognitive capabilities of human. Having said that, so the process in science is to tackle one problem. We always need some kind of benchmark to assess, or in case of machine learning or artificial intelligence, to base our training on, or evaluate the other models based on the kind of task that we are solving. So far, when it comes to reasoning, a majority of benchmarks and data sets are synthetic, meaning that they are only compiled for a specific task, and most of them are not maybe a real world problem, but then they're combined in order to address a specific capability in reasoning that we are trying to solve. When it comes to science and research around this topic, there are four major categories of reasoning that the research is assessing or working on. The main one is, or the majority of data sets are around arithmetic, mathematical reasoning, like solving an equation. In today's talk, I will give more examples of the last one, GSM-8K, which is grade school mathematics exams with answers with 8,000 entries. Another one is common sense reasoning and logical reasoning and multi-op question answering. In the next slide here, when I'm giving an example, you will get an idea of what each of these types are. For example, in the GSM-8K that I mentioned, the arithmetic problem would be, there is a question in natural language, something like, James decides to run 3 sprints 3 times a week. He runs 60 meters each sprint. How many total meters does he run a week? And we would like our models to be able to solve such equation, and the final answer is 540. And also the data sets or the benchmark gives the rational, like, or the step-by-step path to get to that answer. Another type is common sense. So let's look at these 3 examples from Common Sense QA. One example, the first example is, where would I not want a fox? Hen house, England, mountains, English hunt, California. So just by looking at this question, you may sense that common sense as a problem that we are trying to tackle is very much cultural and language based. So not only the model, we wanted to learn the context around the world that we are experiencing, such as what is fox, what is hen, what is the relationship between fox and hen, predator relationships that they have, and also some cultural maybe information or context, such as is there any relationship between England and fox, or California or fox, or other animals or wildlife in each of these countries, or even what are they? Are they countries, or name of places, or name of the people? So if you remember, I gave the definition. One of the definitions to reasoning is to claim something is false or true about our world. But then we need our models to be grounded on the world that we know and we are interacting with. So this makes the whole task of reasoning much more complex, and this benchmark is one way to assess the common sense in that case. Another type of questions the benchmarks are deductive, where we have like related from a natural language question, we want to see what is the relationship between the people. Like in this case, Christine and her son Justin went to visit her mother Carol. And the question is, how is Carol related to Justin? The answer would be Carol is grandmother of Justin. And in this case, the language model or the reasoning model needs to understand the family tree from the sentence. And maybe there are pronouns like her son, her mother, that it needs to disambiguate who it is referring to in a language. And plus some common sense, common knowledge that is Kristen a male name or female name, Justin is a male name or female name, or how the whole family tree works. So these are very easy for us, but of course it's not. These are all that a model should know or understand in order to answer this question that maybe does not seem to us. Another concrete example is from multi-hop question answering, where given the retrieved passages from Wikipedia about a topic, for example, in this case, Theodor Hecker, born on this date, Harry Wagen Watkins, born on this date, and then the question is who lived longer, Theodor Hecker or Harry Wagen Watkins? And so the question, this requires multi-step reasoning compared to if I just ask, let's say, how old is Theodor Hecker? So you, from one passage, you could get that information that you have a date, and maybe your model could understand that there is what is the relationship between age lived and the birth date. But then when we want the model to be able to compare and assess and judge and evaluate the differences to say which one was older, there are many underlying reasoning steps that we are going to, while we as a human, even we are not considering. So from this survey, I brought the list of all the data sets and benchmarks that scientists in this area are using or have been using since 2014. The topic of reasoning is not new, but I would like to bring your attention to this fact that when you see the applications of AI in your daily life, for example, we see speech-based assistants like Siri, Alexa, or we see machine translation applications, or even searching and retrieving a concept, something that related to a query. So these are all goes under umbrella of AI, machine learning, and all topics, and then which we have seen daily. But when it comes to reasoning and the application I mentioned, like planning, long-term and short-term planning, or problem solving or deduction, we have seen less application, let's say, or at least democratized application that everyday people use outside science community. There had been some challenges in that regard. Some theories might be explaining why it's the case. One aspect is lack of generalization. In the previous one, in previous slide, I listed all the data sets related to reasoning. The models in the past were addressing this problem would most likely only solve one of the benchmarks challenges, and then the same model could not be applied to others easily, because there were lots of underlying assumptions they would take about the type of questions that were not generalizable. Similarly, in the past, our research were mostly seeing reasoning as a logical and math-heavy step where, for example, you have propositional logic, like from fact P, if fact P applies, then fact Q, and go on. This later on, especially after especially when I mentioned the example of common sense reasoning, you will notice that much of reasoning task or much of reasoning problem is very much language dependent. And solving it from mathematical or logical point of view had some challenges, and some common sense or some aspects of reasoning were not seen or applicable in that case compared to language modeling. So the whole topic of reasoning got again to more alive when with the advent of language models. So not only large one, but even from earlier research on LSTM architecture or sequence-to-sequence architecture, we see again some research back to topic of reasoning and trying to solve the reasoning. But actually, we did not have much big breakthrough until recently when we got to large language models. So that's why from here, I will talk about larger language models from two different lenses, actually. So the rhythm of our talk at this point might change slightly. One is, so from now on, I will go through some of the important papers and research papers in this area of reasoning, especially on large language models, especially on topic of GPT models and GPT architecture. And so my first goal is to give examples of reasoning in LLMs and how LLMs are solving the reasoning problems that I mentioned their benchmarks earlier. So the goal is, can we have better AI applications that assist human regarding with these reasoning capabilities? Then we want to solve some reasoning tasks such as arithmetic questions, long-term planning, some problem solving, deduction, comparison. But then there is another lens that I wanted the audience here to get to, or which is more thought-provoking. The fact is, in science community, let's be honest, we are not sure why LLMs could reason. So we see evidences and we are trying to experiment with these different evidences to see to what extent they are reasoning, but there are so many open questions why actually they are capable of reasoning, and what happened that they were not like our previous models or smaller models, they were not able to reason to some extent, and now we are seeing a kind of breakthrough in those areas. So these open questions kind of probe us to maybe revisiting some of our understanding of human cognitive ability, or even helps us to understand LLMs after the fact. Like maybe we understand why such a mathematical model can help in other tasks such as reasoning as well. So I want to start with the first paper, Chain of Thought, which addresses the same set of reasoning problems. And as an example, in the paper, you will see examples of arithmetic reasoning, common sense, and others. But here I'm bringing you one example from GSM-8K that I mentioned. It's an arithmetic problem or equation which is in natural language, and then the model should get to the answer. So when asking let's say earlier models of GPT-3, so not 3.5 and not GPT-4, but the earlier models, DaVinci 1 or DaVinci 2, if you're familiar with. These models, given this a simple mathematical question, like a juggler can juggle 16 balls, half of the balls are golf balls, half of the golf balls are blue. How many blue golf balls are there? So the answer is, and then this would be the prompt, and then you would probe the language model to answer. And the answer, for example, is 8, and you can see that it completely hallucinated, like it given an answer which is not correct, and you do not even know why it would produce 8 instead of the correct answer, which is 4. Okay, so chain of thought argued, okay, so in large language models, sometimes it improves when we give some examples to nudge the answer. So which we call few shots. These examples we call shots. With few shots means that you give a few examples in the prompt. So let's say if we say, okay, we have a question and the answer is, for example, 11. With a new question, can it answer? But it did not help. And in fact, only with the GSM 8K, only 17% of times it could answer such questions, which is not high. Then they tried something else that kind of changed. It was the base of our changing our perception of what is happening and how the models are reasoning, or maybe not reasoning even. Instead of giving an example that the answer is 11 for the first question, it gave as an example, it gave a process to get to the answer. Like Roger has 5 tennis balls, blah, blah, and the answer, the example answer is Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 balls. Therefore, 5 plus 6 is 11. Then the answer is 11. So the process how it got to the answer. And then when given the new question, the model could answer correctly, as well as the rationale how it got to the conclusion that the answer is 4. And actually, the number of correct answers in this case in the benchmark GSM 8K improved from 17% in the previous slide to 46%, and which was even better than fine-tuned models specifically for that data set. So what does it tell us? One is, okay, so we dramatically see the improvement in reasoning quality or reasoning performance in the model when we were asking for the rationale, or we were asking the model to give the rationale. But to be honest, this method had not worked in the previous version, a smaller version of LLMs. So in the picture on the left, we have on the X axis, we have the size of the model, like the model as we went, the parameter size got scaled. And for example, GPT Da Vinci 1 or 2 had 175 billion parameters. And Palm similarly, and Lambda similarly, over time, their number of parameters increased. So you see the blue line is with chain of thought, and the black line is without it, like the normal prompting that we see in the first slide. Then until several billion GPT did not show any improvement. Like there was no difference between chain of thought and a standard prompting in that case. It was after a specific scale, like more than 7 billion, that suddenly, like when we reached to GPT-3 with 175, suddenly dramatically chain of thought improved. These examples to give rationale improved the result of reasoning. So what we learn is that that's why we call, or this paper claims that reasoning is an emergent capability. And emergent means that when we change something quantitative, but actually something qualitative suddenly appear. So we only changed the scale, and suddenly reasoning appeared in the model. So these are a few emergent capabilities that larger language models have. And not only reasoning, we have been seeing other capabilities that suddenly, when you increase the scale of the models, the capabilities suddenly appear. And to be honest, we don't have yet insight on why is that the reason, although there are some theories or hypotheses, but not proven. So lesson number one is that nowadays I use almost all the time whenever I'm solving a task or I'm creating an AI based on prompts or based on the GPT models that needs reasoning capabilities. I always prompt it to give the rationale. And then, so this will improve the capabilities and performance by itself. But secondly, I will also use it to debug my prompt. So I'm writing a prompt and for a specific task to solve. Sometimes it works, sometimes it does not work, and I want to know how I can improve it. So by saying to tell me your rationale, when it writes the rationale, I can get, oh, okay, so actually it got to a wrong answer because it's interpreted this part of my prompt wrongly, and then I can improve it and make it more clear and move from there. So practical learning out of it is to you can use these kind of chain of prompt to probe the model to give the rationale why it shows. So it gives a power of interpretability to the model. This was one. Second one, as I said, it seems that chain of thought and improving reasoning only happens with larger language models. I said I'm looking at two lenses. One lens now would be, does this open question that why this gap happened would give us some insight about human cognitive capability. So there is a type of Piagetian theories of cognitive development in human, where the argument is reasoning dramatically improves when we age to adulthood, or the child has less capabilities, and it actually reasoning develops later in development of our cognitive development. So in the neo-Piagetian theories claim that these changes in reasoning with development come from increasing working memory capacity. So it seems even in human, it might be aligned with this theory, what we are seeing, that the larger memory capacity human has, or the model has, probably the reasoning, the better the reasoning it can bring up. So this was the two lenses from this point of view. There is another interesting paper following the same paper. So on the right side, it's the same as chain of thought paper, like we are giving an example how to give rational. But then later on, the paper large language models are zero-shot reasoners actually found out that if you do not give those few examples, and just at the end of your model, you just prompt, let's think step by step, without giving any other processes. Just by nudging the model to give its rationale before giving the answer, it could produce the answer much better. And actually, there are two interesting facts. It improved from 46% to actually 78% of the times for GSM-8K benchmark that I mentioned. It could improve the answers dramatically, actually. And another interesting aspect is that they not only experimented with one sentence, let's think step by step out of blue, but then actually they tried few different hinge parts. They tried without any hinge prompt, and they tried with some completely irrelevant first token, let's say abracadabra. And so you can see not only, so in some cases it also decreased, like if you don't give abracadabra, even you will end up with a better results than giving some irrelevant answers. irrelevant prompts. But then another point was it also gave some misleading, not wrong, but then misleading ones, like don't think, just feel. And you see a slightly improvement in the results, but then it's still very bad. But another example, by using the fact that Earth is round, completely irrelevant fact, you will get even to like much worse results than zero shot without any example. But then let's look at some instructive examples. So the best one was let's think step by step. And then, but there are other candidates like first something and then go on. Let's think about this logically. So they all almost got to better results or good results. So what does it actually tell us? One is we guess, we still, as I said, we don't know, and there is no proof that, but then this there are some theories, hypotheses, and that how this works, and then we need much more experimentation to actually get to why this is happening. But then there are two theories. One is actually in context learning, meaning those few shots that we gave in chain of thought compared to this one actually might be bringing some biases that distract the model from the answer. So if the few shots or few examples is relevant and in the same direction of the question that is being asked, it might improve it, but then it reduces a tiny bit of generalizability. This is something that we need to think of. Then another hypothesis is that it is about the rational at the beginning. Why giving the rational steps at the beginning actually is improving the results. There are two hypotheses in that regard. One is actually models like human need some time to think. And these extra tokens, either in the prompt or in the generated tokens, will give a tiny bit of time or computation. So each token to calculate each token or come up with infer each token, it is going through some calculations and kind of attending to some of the words in the prompt or in the knowledge. So by producing this rational at the beginning, actually we are making it to think a bit, we are giving it time to think than just asking the final answer in the first token. Another plausible hypothesis is that similar to fine-tuning, meaning that giving new training data to actually change the state of the model for a specific task, actually each token is playing almost like you're fine-tuning. So kind of it's bringing a bias to the system that this generated token is relevant to the next one. So sometimes it can be helpful as similar to fine-tuning in this case. So this was lessons that we learned. There is another paper, and I have to be fast because we are almost out of time, and I want to get to also Q&A. So in this paper, even with chain of thought, even with the rational, you saw it only gave 46% without the let's think part. Let's think a step-by-step part. So in the cases that it's getting the answer wrong or even the rational wrong, this paper probed the LLM slightly differently. So instead of going with the rational in language, natural language, they prompted in a way that it produces the steps in like Python language or a specific programming language. It improved the results, although for arithmetic mathematical, the improvement is not much high or let's say significant. But then when it comes to multi-op question answering and logical inference, it dramatically seems to be improving the results. There are two hypotheses why it is working and what we learned from. One is probing to give the tokens in a programming language is actually a context, it is like to prompt a language model like you are a programmer, you are a mathematician. So the context mathematics or programming languages kind of give the context or biases the system to go into accuracy mode, which is what I call like it will probe the model to be more scientific compared to natural language, simple rational in natural language. So this is one aspect of it. Another reason that we sometimes use this part is that we use this technique to verify the results. So when you have an application in future in AI deployed serving people, you cannot just look at the results and see if it is true or not. Should I send it to the human or not? You actually need some automatic verification. So having an answer and process to an answer as a programming language helps you to auto verify it. So this is a common practice that we also do in applications that that are possible, that you can make a programming language out of it. So there are so many more verification. So as I said, it's a huge topic. You can train a smaller model. You can do multiple steps to verify the results, but then it helps the auto verification when it comes to applications. Another interesting paper that I wanted to mention, and then the next one, just to give you a pattern of what is happening, is that in the model, in the paper Self-Refine, so the architecture they designed is consisting of two different LLM calls. One is specialized in answering a topic, let's say mathematical question answering, and the other one is designed for giving a specific feedback. Like in case of mathematical one, what is the code like in case of code production or generation, what is the code how do I optimize the code? And then when it comes to feedback, when it comes to, let's say, other topics like common sense reasoning, the feedbacker or feedback LLM is specialized to give feedback, constructive feedback. And these two models pass each other answers, and therefore over time, after a few passes, they realize that the answer to the reasoning is much improved. So this is one technique that I will dive deeper in a second. Similar to this, also least to most prompting is consisting of two different LLM calls. One is specialized in breaking the task to a smaller one, and the other one is specialized to solving each subpart and then going addressing each one and go to the next. So you see, again, two different LLM calls passing each other can improve the results. This brings me to a future of research that I am seeing right now, the trend that I'm seeing right now in future, and we will see more applications coming on this topic. And that's the topic of multi-agent to collaborate to solve a problem. So similar to human, each of us has a memory and a bunch of knowledge that we carry with us that another person might not have. So when given a reasoning task to each of us, we go through our individual memories and might give a different answer based on our experiences. So similarly, if you have multi-agents with which are specialized or have different memories and they are prompted differently, when they are together like human to collaborate and each bring their unique expertise, unique memory, then you can actually revolutionize maybe some of the tasks that we have not seeing great results in yet. So this is the future that we are looking into. And finally, the messages to take away. So I hope you take away what is reasoning and what future AI products it can unlock, and why it was very close to my heart and why I brought to you today. Another one is some of the ways that the LLM work that surprise us, let's say, and by surprise I mean we did not expect it. We did not know that much about human cognitive, and now we are comparing. It probed us to many open questions around even our capability, not only LLMs. So that part is interesting, and I hope you dive into and ask yourself and go explore. And finally, all that I mentioned and all the celebrations we are making in some progress we are making in reasoning, actually the reasoning task is far from being solved, and there are still so many papers to come, but let's acknowledge we had a breakthrough, and that's why we are excited. I hope this is what you get into. And finally, I want to thank you. And if you have further questions, I will ask for Q&A now to see if there are any questions. But then if there are any, even after the meeting, I know I am only left with 5 minutes of QA. I'm sorry, that was not planned. But then please reach out to me in LinkedIn, and we will have a discussion, and I try to answer some of your questions. So,
Yes,
Shad.
thank you, Shabnam. This was really great and very, very interesting, I think. And we have some questions. First is if we don't know why LMMs are capable of reasoning, do we need a new research area for AI, like anthropology for humans?
Yeah, I think that's a good idea, and I think already there are directions on that area. So researchers from cognitive science, psychology, and also computer science. All there are many groups in different universities already researching and probing that area. But definitely that will be very helpful as we are going and experimenting with LLMs.
Mhm.
So next question I see, if I build a process based on prompts that give me the results I want from the model and the model is evolving, how do I make sure the results stay the same? Okay, that's a good question. And actually, this is a valid challenge that we have with large language models, consistency and reproducibility. So right now, we have this challenge, like not all the time given one prompt you will get to the same answers, but on the same direction of verification, there were two slides that I jumped, but then you can go through and look at them. There are processes that you can use to verify and get to more consistency compared to what we have right now. For example, I encourage you to look at the paper diverse, and there is the other one, self-verification. So this will explore different paths, different reasoning paths, and basically it's claiming that LLMs have self-consistency, meaning that although one or two results might not be consistent with the rest, but then if you probe multiple paths and take a majority vote, you will get to more consistent one. Another thing that I can say, and we are recently working on, is that with the multi-agent paradigm that I mentioned, with one inconsistent result, the other agent can fix or give feedback to the agent that, oh, this was not what I expected, and then the model can correct itself, and this also resulted to more reliable and consistent results when it comes to prompt engineering for us. I hope it helped.
There's another question.
Okay. There is another question.
Yeah, self-refining using self-feedback sound very promising for specific use cases, but also vulnerable for bias. Is the best way a mixture of different approaches?
That's a good food of thought. I really would like to know what you mean by improving biases in this case. But from what I get, and I think one aspect that you can say is that the feedbacker, the agent that gives feedback, you have to give or prompt a specific metrics defined by human how to evaluate those tasks. At least that's what this paper did. In that case, yeah, I can imagine you're limited to those specific metrics, and it's still in that case it improves the model, but we are still far from solving the problem that I mentioned. So you're right. It's still there might be biases. It's still with the self-refine. We might not get to the perfect results, but the research has shown that the performance has been improved.
Mhm. Okay. One second.
I also build processes using automation tools and ChatGPT and try to make sure the results stay above a certain quality level. How would you approach this? That's also a good idea. I think with even at Microsoft with even OpenAI or even Microsoft Copilot products, there are many verification steps in between. So you would get the results or output and give it to another model to make sure it is following responsible AI, it is following the safe AI guidelines, and based on that, you would block that answer or retry again. So when you're designing your product, these are something that you can design or think about. Yeah.
Yes. Here is now the specification about the other question before, because you were asking about the bias thing.
Mm-hmm. So I meant that if they're moving in a total wrong direction, then they would self-feedback them further towards the wrong direction. I thought about race bias. I need to think about it and see some evidences or researches around this idea. But generally, we are the ones who are aligning the LLMs. Like even like current models of OpenAI are going through very true processes to align the results with the values that we have, like racial biases and anything in that regard. So I guess there is this risk, but to avoid it, we can address it in multiple steps. One is at the time of training, with given the training data that we are giving. Another step is by verifying to make sure that a result specifically does not contain racial biases. So you can have a specialized agents and a specialized training data or LLMs trained on a specific safe set of data sets just to test for that. So that will make sure that this does not happen and the model is aligned with our values. So there are many guidelines you can implement, and there are practices that we are also following when we are producing our products. But that's definitely a great point.
Okay, thank you very much. I'm just looking if there are any more questions. I think there are not. So then I will thank you very much for this speech.
You,
It was
Shab.
really great and very interesting question as well. I think this is a very interesting and absolutely state-of-the-art field of research. And thank you very much for giving us these insights. Thank you very much. It's our last deep dive session. If you want to say anything for goodbye, please feel free.
So thank you so much. I'm also honored to be here, and I'm amazed by all the great questions that people are asking. Honestly, I'm also moving. Now I'm in office in Berlin, but I'm moving to the venue itself. So probably I can meet more people and continue the discussion. Looking forward to that.